So next we need to make our circle shape, our first shape in our ShapeMaker script. So there's a few things we need to learn about GLSL here, and it has to do with kind of packing and unpacking this vec4 constructor that we made right here. This creates a new vector4 kind of like object or data type, if you want to think about it that way, even though it's just kind of a container that holds these other values. So the first thing to know in GLSL is that you can create your own vec4s. They don't have to just be assigned to frag color right away. You can actually create another placeholder kind of value, and that's called a variable. And so this variable actually kind of like holds some values, and then you can refer to the variable later. And again, if you're used to computer programming, probably the idea of a variable is kind of the first thing you learn about. When you create a variable, you have to declare its type. In this case, the vec4 is a variable type, and I'm going to give my variable a name. I'll call it color. And color, I'll just take what I've got down here, vec4. I'm just actually going to copy it and paste it up there so that it's been assigned, and then I can replace this with my reference up above, color. And I go ahead and execute this, and it's working. So something that's kind of interesting is if you want to get the components out of a vector4 object, there's a ton of ways to do it inside of GLSL. And actually, this is something that's a little bit different than maybe some other environments you might be used to. So there's labels. So color, since color is, we've got 4 numbers, and it seems as though that they're kind of color values. Color.r will actually refer to this first value. Color.g, color.b, color.a, just as you might suspect for red, green, blue, and alpha respectively. So, if I wanted to just like take color A and like kind of repack it, I could. But surprisingly, actually, there's also some other labels. Color.x, y, and z, x, y, z, also refer to these first 3 numbers, which is also kind of interesting. And if you wanted to return 3 of the numbers, you could say color.rgb or color.xyz. XYZ are typically the labels we use for a coordinate system, and RGB are what we typically use for a color system. But actually, GLSL doesn't discriminate between these. You use vec4s for both, and so you can freely kind of, swatch kind of what's called swizzle between them. And this is, I think, swizzling is it's kind of a fun term. It's kind of fun programming, but it's really more about kind of like swapping, right? So you could say RYZ. You could say R, let's say red, green, blue. You could say red, blue, green, and actually this will swap those. This will swap those values. You can go ahead and get those values out and rearrange them however you like using Swizzle, which is really fun. You can also use, let's see, there's STUV, which is another set of labels, and one is kind of used. XYZ is kind of typically used for like 3D coordinates, vector math, and STUV is typically used for UV coordinates, 2D, and RGBA, of course, is used for color. And then something else that's kind of interesting here is you can also just pull them out using their indexical places, like 0, 1, and 2, as you might be more typically used to, maybe using arrays in JavaScript or processing, for example. So lots of different ways to get at our values in GLSL, which is kind of interesting. There's other things you can do too, which are interesting as far as construction is concerned. So like, let's say I have a new vec3, and a vec3 is only going to hold 3 of these values. And that's where I'll hold the R, G, and B value. And this is really common. We're actually going to need this. So I declare the vec3 color here, and I'm going to ignore this for now. I'm going to get rid of that. And then here inside vec3, I'm going to label these as 1.0, 1.0, and 1.0. And then down here, watch this. This is something that's kind of interesting. I can say vec4, and I can just like put that vector3 inside the vector4 and actually compile, so it doesn't have an error. I can just say color, and then I'll do a comma, and I'll say 1.0. So this means that my alpha is always going to be this 1.0, which is what I want. I want it to be always be on. And then I want to be able to control the red, green, and blue colors. And this is actually also really common workflow. So let me go ahead and we'll make something that's just green and blue. It just has the green and blue. We'll save this and then we'll test it. And we're going to get this aqua. So color, I've got now kind of its own color control. And so the compiler is smart enough to take this vector3 and kind of like put these things in their places, their respective components. Another thing that's kind of interesting is there's some other shorthand that you'll probably see me use, and I can just type in 1.0. And actually, the parser is smart enough to recognize that if it's just one argument, it'll go ahead and actually put them in all three components of the vec3 object. So this also won't throw an error. So this is kind of loosey-goosey. I actually really like this, that you can just kind of, one thing can become all things. You can freely kind of mix and match and pile stuff into different vec4s, vec3s, kind of get stuff in, get stuff out. And you'll see me kind of doing a lot of that, so I wanted to make sure that I mentioned it. And in fact, this vec3 color equals vec3 1.0. Let's go ahead and let's hold on to that variable. That's going to be useful for us. Okay, so the next thing we need to do, besides just send a color to all these pixels, is to get the individual values out of the pixels. And by this I kind of mean their coordinates. Again, if you're probably used to, CPU programming or different other styles of programming, what you're probably used to doing is looping through an array of pixels. Like the pixels are held in some sort of data structure, and then you loop through that data structure to query their individual values. But actually, in GPU, and in the GPU land, in graphics programming land, it doesn't work that way at all. It works with something called parallelism, which means that actually all the pixels get kind of processed at the same time. They don't know anything about each other, about the other pixels around them. So you could say that GPU programming is stateless, and they are kind of all processed together. That's why we call it parallel or multi-threaded. So this is kind of mind-blowing. This actually, for me, the first time I came across this, I thought this was almost like magic, particularly if you're used to, as I mentioned, other styles of graphics programming. So how can we get all of these values? Well, there's a call for this in GL. So we'll call this, let's make a new vec2 object, and we'll refer to the screen space, the space of the screen. So this will give us the value of the pixel values in their coordinates, and that will be equal to GL. And then instead of frag color, we'll say frag coordinates. There we go. So the screen space is the GL frag coordinates, and I'm going to get just the X and Y values. And this has vec3, so let's go ahead and let's say screen space dot X. Let's get just the X values. And then let's see if this works. Because it's going to blow out totally to white, because actually these numbers are 0 to 1 for color, but these numbers, the coordinates of the screen, are going to be really big. So what we're going to do is actually we're going to normalize these values. So from X to Y, we'll divide it by the size of the render. And render size is what's called a uniform. It's a global variable that's been created for ISF. So when you're using the ISF environment, you can call render size, and you can tell that it's an ISF variable. It's here in this capitalized formatting. And it will return basically the size of the screen. So in this case, it's going to be, I believe, 1280 by 720. So this is going to return the values of each of the pixels, where their coordinates are, and it's going to divide them by the size of the render as an overall. So what this will do would be, let's say, for example, we're looking at the center pixel, which is 640 by 360. So 640 divided by 1280 is 0.5, and 360 divided by 640 is 0.5. So that's going to basically remap our coordinates from the size of the screen to 0 to 1. And for that reason, we call it normalized coordinates, right? We've taken a number and we've made it become a range of 0 to 1. And as it turns out, that 0 to 1 range is going to be really useful for us because we need a value range of 0 to 1 to draw color. So let's go and save this and see what this looks like. Okay, very interesting. Now you notice we have a gradient here. Now again, all of the coordinate values, all of the pixel coordinates are being returned all at once. This code is being run for all of the pixels. And so this frag coord call is really kind of magic, right? Like this is saying like, hey, take your individual value and plug it into this, basically into this variable. And so this little bit of code runs on all of the pixels all at once. And so rather than kind of looping through them all and then setting a bunch of conditions and seeing where they are, so you can see why actually why maybe maybe up until this point you might say like, well, why do I have to learn all this ISF stuff? I can do graphics programming in a lot of other ways, and this is why it's going to be a lot more efficient. It's going to be a lot faster. The graphics card, it can only do one thing, this parallelism stuff, and as it turns out, it's really fast. So screen space is a vector 2 coordinate. So let's go ahead and we're just pulling the X out and mapping it, remember, to the red, the green, and the blue in this case. And then let's go ahead and let's just try the Y. And as you might suspect, if we update here, we can see that it's the 0 to 1. Now, something that maybe you've observed that maybe is a little confusing. I'm just going to create a second layer here inside of VDMX, and I've prepared a couple just quick overlays for us to think about these values. This feels like maybe it's backwards, right? Like it seems like the top should be black and the bottom should be white because it's going from 0 to 1. And I'm just going to go ahead and trigger this in layer 2, the layer I just created, and then inside layer 1, I'll overlay our, I'll trigger our ISF that we just created. But actually, no. ISF and GLSL, of course, here in this case, are going to start counting 0 from the lower left-hand corner. And this is actually, this kind of makes sense if you just think about just kind of like counting up and counting to the right. That if you're used to other types of video creation or layout software, like say After Effects or Photoshop or Illustrator, the upper left-hand corner is 0, 0, and then that gives us always positive numbers as we count kind of down to the right. But lots of other environments, graphics creation environments, kind of have 0, 0 be at the middle, right? Like kind of like the middle. And in this case, we have it in the lower left. And this is kind of more if we want to do more like mathematics environments or a graphing calculator or, Excel or something. So right away, what we might want to do is try and remap our values to make 0 be the center. And, like probably we'd want to get something kind of that looks more like this, or maybe even something that looks like this, like, 0 in the middle and then 1 on the right and 1 on the left. You might think this is what you want, and sometimes this is what you want. But there's some advantages to making everything be 0.5, negative 0.5, positive 0.5, 0.5, 0.5. That means it's still a unit of 1. And this is also sometimes called a unit vector because it's from 0 to 1. It's still a unit of 1 from the left side of the screen to the right side of the screen, which makes all kinds of things possible for us. So what I'm going to do is go ahead and I'm going to trigger here in layer 2. I'm going to remap our coordinate system so that 0, 0, instead of being in the lower left-hand corner, is actually at the center of the screen. And this is really easy to do. I can just take screen space, and I can just subtract 0.5. I can just minus 0.5. And you could say screen space dot x is equal to screen space dot x minus 0.5. And you could do the same thing for the y, of course, if you wanted to deal with these as like individual components. Or you could just say, okay, that's a lot. Screen space is a vec2. You could just say screen space is equal to screen space minus a new vector 2 object, and that's 0.5 comma 0.5. And you'll see me sometimes omit the 0. I find it best practice to just write the 0.5. It helps keep me from getting confused with the comma, but it's not necessary for it to compile. Or, of course, the shortest way of doing this is to use our assignment operator, which is that, hey, we're going to add our math minus equal, so we can right away just say like, hey, screen space minus equal 0.5, and actually this is smart enough to take this 0.5 and subtract it from both of the components of the vector 2. So this is the most efficient way of writing this. Again, you'll see me do some of these things, so I want to make sure that I mentioned them. And let's go and let's save that, and then let's reload that. And aha, there we go. Black is now kind of here at the bottom, and it goes up to here to 0.5 at the top. Okay, so let's test this out also with X, and my expectation is that the black would begin in the center, and sure enough, it does. So we've remapped our coordinate system to having 0 be in the middle, and this will be useful. This will be useful for us. We'll come back to this actually. Okay, so then now the next thing I want to do is notice the screenspace.x and screenspace.y. I mean, we can have all kinds of fun with this. Like for example, I'm just going to forgo this color here. I could say screenspace.x, screenspace.y, and let's do 0.5. So this vector 3, rather than using screenspace.x, for all the three, red, green, and blue, I've broken out red, green, and blue to the different values. And so let's take a quick look at what this looks like. Let me save over here, and we'll refresh. And look at that. Okay, so we've got like red, green, and blue do all kinds of doing different things, right? Like one is kind of remapping along the x axis, one is remapping along the y axis, and then they're all blending together. So right away we can make like gradients. You can also just do simple math with this stuff. Like you could just say, maybe screenspace.x, and let's just multiply screen space.y and see what happens. Okay, and look at this. We have these really interesting results where we have these little gradient, like kind of globules actually, like kind of in the upper right-hand corner and the lower left-hand corner goes to 0.5. That's because 0.5 times 0.5 is going to be 0.25, and then we're going to have this interesting fall off as it goes to 0. I mean, let's try divide and see what that yields. And again, yeah, something kind of interesting, right? In the negative components, in the negative quadrants, there's nothing, and then we get this like interesting kind of slice in the middle. And you don't really have to know math to just mess around with these things, right? Like you don't have to really think about like, well, what's the result going to be? You can just try it and see what happens. Like for example, you're like, I think I want the opposite of that. Then why don't I try multiplying it from 1 since it's a value from 0 to 1, and that'll give me the inverse. And my point here is that you don't actually really need to know a ton of this math to kind of like use a little bit of logic, right? And also you can kind of just fiddle with these numbers until you get interesting results up in here. I want to make sure that you feel as though you can play around with these things and try them. Okay, so the next thing I'm going to do is I am going to actually follow some formula in here that are going to be useful for us for drawing our first shape, which is going to be a circle. And I'm going to actually, for now, I'm just actually going to forego the resetting of the screen space. So it's actually, we're going to come back here to this coordinate system of 0 to 1, and I'm going to get rid of the 1 minus here. And let me save here and make sure that this gets triggered in layer 1 and layer 2. So we're back here, we're right back before we move the coordinates up to the center of the screen. So we've got 0 over here to 1 over here and 0 to 1 there. Okay, so we can actually start doing some mathy stuff. And what we're going to do is we're going to do some math that is figured out thousands of years ago. We're going to do the Pythagorean theorem, a squared plus b squared equals c squared. And this is actually going to be really easy math for us because basically what we need is an a and a b. And actually a and b in this case are going to be x and y coordinates. So the x coordinate this way is going to count along this axis, and the y coordinate is going to count up and down. And then what we want to do is get the length between the two values. So that'll look something kind of like this, right? Like, okay, here's our x. Let's say our x is 0.5 and our y is 0.5 up to here. Then just return that value, which is the length of, well, it's the length of what's called the hypotenuse. You don't need to know any of that. In fact, you don't even really need to know, this. But let's just do it. Let's just try out a squared plus b squared equals c squared and see what happens. So let's type in that formula and see if we can get a useful result. So let's see. We need the a square is the same thing as saying a times a to the exponent of 2. It's just the value multiplied by itself. So that's a. That's screen space.x, and it's multiplied by screen space.x. And then if I want to make sure that that happens with order of operations. I can use parentheses to force this to happen, make sure that these two values get multiplied together. And then I'm going to add a screen space dot y times screen space dot y. Great. And now I need that gives me the result of this, but the result of this squared. So you could also say actually c is equal to the square root of a squared plus b squared. Using algebra, we can like get rid of this the square sign here and actually just add it as a kind of a square root over here on this side if we wanted to isolate the value of c. So we have a function for that, square root, just like a graphing calculator. Okay, so there's our formula right there. And let's go ahead and let's say let's create a value for that called now this is going to be a single value. I know this is the part that gets a little confusing because actually this is going to return a float value. Like this c is a single value. Even though we're giving it an x component and a y component, we're deriving a single value. And we're going to derive a single value for all of the pixels in our frag coordinates. So float, the distance is equal to, very good. Now this right here, remember, this also is a float value right here, the screen space.y. This is returning a single value for all the different pixels. So I can just pipe in distance here and save, and let's see what happens. I'll come here to layer 1. And okay, so something kind of interesting happens. You'll notice that this actually makes something kind of like a circle. And it's not something like a circle, it is a circle. This is actually going to return a bunch of values that look like this. And actually, let me go ahead and attenuate this. Let's do distance, and we'll times this by 0.2 to make it a little darker. And I'll come here to layer 1 and trigger that. Very good. So this is going to happen, actually. You're going to get a result that kind of looks something like this, as these triangles kind of step up and step down. They actually describe a circle. And actually, this is trigonometry. This is why these are sometimes also called the circular functions, right? And so this is going to return a gradient that is kind of like a radial gradient. So we learned how to build a radial gradient. Well, that's great, you say, but radial gradient, gradients are cool, but how can I actually make a shape? Well, this is going to return a single value. This distance value is going to return a single value for each of these different pixels. And so you could just test that value and see if it's beyond a certain threshold. And if it is, then you could have, say, a variable be one value. And if it's not, then you could have it, say, be another one. So let's go ahead and let's try that out. Let's say float color. And actually, let's just give it a value of 1.0, and color if the distance is greater than let's say 0.5. If the value of distance is greater than 0.5, then color, and let's start with a 0 value of color. Then color is equal to 1.0. And if the distance is less than, and let's reverse this. Let's have less than 0.5 and greater than 0.5. So the inside of the circle will be white. Be a little easier to see and understand, I think. Color will be equal to 0.0. And then I've created two variables here. One's called color, one's called color. So let's go ahead and let's just call this circle. Circle threshold, maybe. Circle threshold. I like long verbose variable names. Let's just call this circle thresh, right, like that, just because I like to go back and read these things later. But probably most of the code samples you'll see will be one letter. Like, for example, they'll use one letter to represent these things. This is very common, like float C. Okay, so let's see, circle thresh. Let's come here and let's type in circle thresh. Okay. And let's then go ahead and trigger that, and look at that. Interesting. Okay, so when it was below this 0.5, it bumped up to white, because it's past that threshold, and when it's beyond it, it's bumped down to 0. Now I want you to notice something. It's kind of like a weird oblong shape, and we'll fix that in a second. So right now, we've got something kind of interesting here. Let me come to VDMX and let's get rid of that overlay. I'm going to come here to layer 2 and eject and just take a look at what we've created. And so far we've got, I don't know, like a pillow. We need to, first of all, put this back in the center. So something that's kind of interesting here is before, when we were doing kind of our mathematical formula, like when we were multiplying and multiplying, we were getting different values for negative and positive values. But the distance is actually going to return the same if it's negative or positive. It actually doesn't care if it's negative or positive. It'll still give us the same distance value. This is because, you know, -5, the difference between -5 and -2 is still +3. So this is actually always going to return a positive value, which we're going to use to our advantage. So let's uncomment out screen space, negative equals 0.5, and we'll save. And come back over here and retrigger back in 1. And look at that. We've got, again, something that is remapping to a 0.5 coordinate system. Right here, right? 0.5, and this stuff is somewhat in the middle. We actually can't see that because it's white. And there's a few things we can do here to actually, let me, instead of having this be 1.0, let me make this just be something smaller. That'll make that easier to see those coordinates. There we go, 0.2. All right, and there 1, and let's trigger that. There we go, and it's gray. Okay, so actually this is exactly what we want. The problem is actually that our screen isn't square, right? That's our math is completely correct. As you can see, we've got that nice round curve from 0.5 to 0.5, which is perfect. But the problem is just the aspect ratio of our screen. And that's because the screen is a 16:9 aspect ratio. And you probably know this if you've ever worked with HD video, right? It's 1920 by 1080 or 1280 by 720 in this case. So we need to correct for that aspect ratio if we want to have a perfect circle. And it's actually pretty easy to do. All you have to do is multiply by the aspect ratio. And in this case, what we're going to do is just multiply the x by the aspect ratio. We're just going to squeeze the x down. So 0.5 is here and 0.5 is up there. So to do this, we'll take our screen space and we'll multiply the x. And what should we multiply by? Well, I mean, yeah, if you already know your aspect ratio, you could just say like, hey, it's 16:9. And let's go ahead and save that and trigger. And I've made a mistake here. I've put in integers instead of floats, which is something I tend to do a lot. And there we go. Look at that. Perfect circle. We've actually taken that 0.5 and we've squeezed it in according to that aspect ratio. Now, let's say you don't know the aspect ratio, or you know what actually is probably smarter is to say, oh, well, why does that should be a dynamic value. That should be 16 is the render size y divided by render size x. And this way we could change it. And that aspect ratio, oops, I've reversed these, x, y. There we go. That way we could change it. Like we could change this and it will live and dynamically update. So there we go. Okay, so hooray, yes, we've built a circle.